Should start now or? Okay. Can you hear me okay?
Yes.
Yeah. So very happy to be here again. Today I want to talk about organic matter in the universe. We all know that every cell in our body is made up of molecules, and chemists were able to determine that all these living organisms, they can be broken down into molecules, and at first they were all extracted from living things. Like, for example, one can determine we can have amino acids from various kinds of plants and so on, and they are supposed to be have something different, something special. That's a concept called vitality. So that what makes the organic molecules different from, say, a metal or a piece of rock is that they have this separate thing called vitality. Now, however, by the mid-19th century, chemists were able to manufacture in the laboratory organic molecules from inorganic substances. So it turns out that it's nothing special really about the living organisms molecules. Now we think that these molecules, when we say organic molecules, we're just referring to a class of molecules made up primarily of carbon, hydrogen, there may be oxygen, sulfur, and phosphorus, and so on. And that is really no longer necessary to have this concept of vitality. So we don't talk about it anymore. And when we look at the amount of organics on Earth, of course, obviously, we think about living organisms, the plants, the animals, the fish, and so on. And if you count everything in the oceans and on the crust, there are about 2,000 gigatons there. But we also can have evidence for past life, in the form of coal, oil, natural gas, and so on. And that come out to be about 8,000 gigatons. Now, what is not so well known is that actually the majority of the organics on Earth is in the form of kerogen. Now, kerogen is a macro-organic material found in sedimentary rocks. And you can see from here that the amount of kerogen is much more than the amount of organics contained in living organisms or even in the fossil fuels. Okay? So most of the organics on Earth are actually in the form of kerogen. Now, but everything that we have on Earth is the product of life. So either it's from the past life or the present life, but so everything that we do know are the result of life. The question is that, is there organic matter in the universe? So that's the question we'd like to address today. And we used to think that the Earth is unique in the sense that we are the only place found with organics. And although some people speculated there could be organics in the universe, but it wasn't too well received. And what today I'm trying to hope to convince you is that actually organics are very common all the way from our own solar system to distant galaxies. And it's a recent, 2016, I'm sorry, 2016, a recent review. And now the first step I want to talk about are gas phase molecules. These are the simplest things which make up 2, 3, 5, 10 atoms. They are free-flying gaseous molecules, and these were first proposed by Swarovski and Charlie Towns in the 1950s. Now, no one believed them because astronomers thought that if there were any molecules, they'd be destroyed by interstellar ultraviolet radiation. The density in the interstellar medium is so low that it would be impossible to form them by, say, three-body reactions, which is how they form on Earth in the laboratory. So the Charlie Towns were not taken seriously until the development of microwave techniques. Then now we do know there are over 200 gas phase molecules detected in stars and in the stellar media. Now, how do we do that? There are a number of ways, mostly either through the molecules rotating that is turning in different speeds, or stretching. The bonds are stretching in various ways, or bending. So when they have these kind of internal motions, they emit unique signals which allow us to detect them by astronomical means. Now, among these 200 gas phase molecules are every class of organics as we know it, including hydrocarbons, alcohols, acids, aldehydes, and so on. Ketones. Now, this is a typical spectrum with modern-day millimeter wave telescopes, and you can see that there are lots of lines there. Actually, every spectral region is completely filled with lines. There is no continuum. And in particular, there are some simple molecules like methanol have, because of their complex structure, have many, many lines, and they just fill out the spectrum. This phenomenon we now call a confusion limit, because once you reach this confusion limit, no matter how sensitive your telescope is, it's not going to be able to detect weaker lines. Now, so in addition to carbon and hydrogen, we know that nitrogen is needed in biochemistry and amino acids in the nuclear bases. So, of course, we have cyanopolyions and various amines and ethers. So oxygen and nitrogen are also present among the interstellar molecules. Now, people always ask, how can you be so sure? Actually, the spectral resolution are so high nowadays, is the agreement with the lines are within 1 part in 10 million. So once you detect the lines, there's no doubt that which molecules you are looking at. So that includes some very interesting biomolecules. For example, acetamide with the simplest molecule with the peptide bond. We have precursor of sugar, and there are some building blocks for amino acids and also of nuclear bases. Now, however, no amino acid, for example, simplest one is glycine, have been detected, and sugar have been searched and not detected. And the reason is not so much that they are not there, but because of two things. One is the confusion limit, and the other reason is the partition function. Once you have a complex molecule with a symmetric structure, there are many, many energy levels, and the amount of energy being carried out by each individual transitions is getting lower and lower. So our spectrum are filled with simple things like methanol, and then you want to look for a more complex molecule. Even they are there, it is very difficult to detect them. Now, in the solar system, we have some advantages, because in the solar system we can actually go there, we can go to asteroids, comets, we can collect the material, we can bring them back to Earth, and you therefore have ability to do laboratory analysis of the actual samples. Now, in the planetary dust particles, you can collect them by high-flying aircraft, and of course, asteroid, comets, and planetary satellites, you can go there and actually have a sample return. Now, the 1960s, it was the first surprise that in meteoroids, organics were found. And now there are over 14,000 organic compounds with millions of related structures that have been identified. And the fact that the abundance of these organics decreases with the carbon number suggests that these are not byproducts of life. So it's not breakdown of some living organisms, but they were built up from simply biological molecules. So in the past, we used to think that the solar system are primarily made up of ice or minerals, but now we think that they are a large amount of organics. I'll talk more about them later in the talk. And the question is that where do they come from? Were they made in the solar system, or they came from elsewhere? So this is a question we want to address. So So, of course, the planetary scientists, many of them believe that they were made in the solar system, but I'm trying to provide some evidence today that we have direct evidence that very complex organics are being made by stars, and they are being ejected by stars, and they are distributed through the Milky Way galaxies and the early solar system. They have inherited these stellar organics. So this is a Hertzsprung-Russell diagram of the evolution of a three solar mass stars, and the most important thing, of course, is the synthesis of carbon. So in the last 100 million years or so, that stars are able to burn helium into carbon, and these carbon are dredged up from the core to the surface, and they are ejected from the surface of these asymptotic giant branch stars in the form of a stellar wind. Now, so this diagram already showed yesterday. So this evidence of the stellar wind at the circumstellar envelope can be seen by this heavily reddened spectrum, that all the energy of the photosphere is removed from the optical and re-emitted in the infrared. So this star is completely obscured and cannot be seen in the visible. Now, the stellar wind can be, the content can be detected in a number of ways. So one is, of course, by rotational transitions. So it's the same way as we detect interstellar molecules. So we have inorganics, organics, radicals, rings, and chains, and so on. So, I mean, it's quite easy to do. And also by infrared astronomy, we can also detect the solid state modes. So these are vibrational modes of minerals, in particular of amorphous silicates. So they are either due to silicon oxygen stretching or bending modes, and then you can see that the signature of the minerals are very clear. So almost all evolved stars are depending on their oxygen rich or carbon rich, they will have amorphous silicates, or they will have silicon carbide, which is in the mineral found in carbon rich stars. Now we know that the AGB stage is followed by planetary nebulae. So interesting is that are there these kind of minerals in AGB stars. Now this was a total surprise, because when the infrared astronomers looked at planetary nebulae in the 1970s, they took a spectrum, and here comes these huge, strong bands that no one has ever seen before. So these bands are called unidentified infrared emission bands, and they come, the strongest bands are 3.3, 6.2, 7.7, 8.6, and 11.3 microns. So this is in NGC 7027. And almost right after the discovery, there were two papers in Nature, one by Roger Neck and by Julia Willems, and they identified the 3.3 micron band as due to aromatic CH stretching band. Now, it's very interesting. I did a count of the citation of these two papers in Nature, and in 30 years, there are about 20 citations in total. Okay. So no one believed them. They say, well, how can organics be made in stars? But actually, these things are well known by the chemists. You go back to the 60s, the chemists have already been doing infrared spectroscopy in the lab. They look at all kinds of simple organics. They know that there are aromatic compounds which have either stretching or bending modes in the infrared part of the spectrum. So these bands are not only seen in planetary nebulae. Actually, they are now seen in reflection nebulae, in H2 regions, in the diffuse interstellar medium, in external galaxies, and so on. So this is M82, and you can see the same bands, exactly the same bands as in NGC 727 and other planetary nebulae. Okay. So if you go a little further, you can see these bands are also very strong in distant galaxies, all the way out of redshift of 2. Now, if redshift of 2 is 10 billion years old, so 10 billion years ago, we already have organic compounds being synthesized in the universe. Now, not only that, a lot of energy are coming out from these bands. I mean, if you look at these spectra, can determine that up to 20% of the total luminosity in the galaxies are being emitted by organics. Now, because these UIE bands are seen in so many planetary nebulae, and since planetary nebulae are easy to observe, and also they have a very short lifetime. The lifetime of planetary nebulae is only 20,000 to 30,000 years. So if they are there, they must be made in situ. So we know that if you look at planetary nebulae, they have these bands, they have organics, then they must have been made in the circumstellar environment. But the question is that at what stage? Because you look at their precursors, the asymptotic giant branch stars, you never see these bands. So we know that for most of the life of star, you don't have organics, and by the time you became planetary nebulae, all of a sudden you have organics. So when exactly do they emerge? So they are not. So we have a situation that in a young planetary nebulae, you're talking about the dynamic age of about 10,000 years. Then they all of a sudden they change from no organics to a large amount of organics. So we would like to look at the missing link between AGP and planetary nebula phases, because those may give us some clues on where these organics are manufactured. So these are called protoplanetary nebulae, and I don't want to go into the details, but about 30 or so were discovered by Wupu, Swiftneck, and I back in the 1990s. I do show some examples here. So these, I mentioned yesterday, these are all reflected starlight and no emission lines here. And as soon as we discover those objects, we do some infrared spectroscopy, and of course they have the 3.3 micron feature. But not only that, they also have a feature which is almost equally as strong as 3.4 micron feature. Now again, you go to the chemistry literature, this 3.4 micron feature is well known. They come from CH stretching modes, either symmetric meaning stretching this way, or anti-symmetric, which is stretching in this way, of aliphatic substances. So they are either from methyl or methylene groups, and you can see the schematics here. So these features are well known by chemists. So this is a young planetary nebula, and RS21282. This is 3.3 micron aromatic CH stretch, and these are the 3.4 micron features corresponding to either the symmetric or anti-symmetric groups of methyl or methylene side groups. Now, another difference between protoplanetary nebulae and planetary nebulae are the presence of bands beyond the 11.3 micron. Now, the 11.3 micron is well known by chemists as due to a aromatic CH bending mode, which is bending our plane. Our plane meaning is bending in this way. Okay. So now, however, there are several features beyond the 11.3, and again, from the chemistry literature, we learned these are due to CH bending modes, but with a different number of exposed edges of the aromatic groups. Very simplistically, these are smaller number of rings. You have when you have islands of fewer number of rings, you get the additional features beyond the main bending mode, which coming out from say a single exposed CH stretch. Now the third property different is the so-called plateau features. So you subtract the bands and the continuum, and then you are left with two very strong plateaus centered around 8 and 12 micron. And so this is actually quite prominent, that it can be seen in almost every spectrum. And our interpretation of these plateau features are the superpositions of in-plane bending modes and out-plane bending modes of aliphatic side groups. Now, when you have a organic compound, of course, it's not a clean laboratory in nature, so all kind of things, all kind of junk can accumulate. So there are many of the aliphatic side groups, we have some examples here in this schematics. When they bend in the plane, that means bending in this way, they all have wavelengths around 8 micron. When they blend our plane, they all have wavelengths about 12 micron. So if you have a whole bunch of junk attached to the rings, and these all bending, then you have a superposition of bending modes giving rise to a broad, say 2-3 micron wide feature around 8 and 12 microns. Now, so how are they made? Now we know that all these aromatic adiabatics, they only emerge during the protoplanetary nebula phase. Now in AGB stars, we know that they are cyanopolyions, which are easy to detect because they are linear molecules. They are hydrocarbons, whereas a combination of hydrogen and carbon. And then the most peculiar is as the star gets more evolved, you begin to see acetylene. Now acetylene is featured at 13.7 micron. Is only seen in extremely evolved AGB stars. But the good thing about acetylene is that it's a linear molecule, but 3 acetylene molecules will close together and form benzene. So they are precursor of benzene. Now, of course, benzene is now detected in protoplanetary nebulae. They have a vibrational mode at 14 point some feet micron. And also in protoplanetary nebulae, you can see diacetylene, triacetylene. So the scenario is that you first have acetylene, then you group together, form diacetylene, triacetylene, and then you form benzene, and that is the first ring molecule. So the protoplanetary nebula stage is only about a couple thousand years, and that you can see the evidence of first formation of clusters of aromatic rings with peripheral junk of these various adiabatics adding on to it. Now, planetary nebulae are different from protoplanetary nebulae in the sense it is a very hot central star, so you're beginning to have ultraviolet radiation, so that could cause the loss of peripheral hydrogen, the closure of rings, and so on. The situation becomes more aromatic. So this is the quantitative scenario of the formation and evolution of the organics from the AGB to the protoplanetary nebula stage and then to the planetary nebula stage. Now there is a tremendous advantage of looking at circumstellar chemistry because of simplicity. First of all, we have a single energy source, namely a star in the middle, and we know a lot about the star. And we have a simple geometry with some degree of symmetry. And also the environment can be determined by other means. We know about the density, the temperature distribution, even the radiation background. Now, most importantly, we know the time scale, because when you have AGB star, you have a stellar wind, you have dynamic age of about 10,000 years. We have protoplanetary nebulae, they only last a few thousand years. In the planetary nebulae, only a couple tens of thousand years. So whatever chemistry that is taking place must be doing it within that time scale. So we are talking about extremely fast chemical synthesis here. Now, let's be precise about the UIE phenomenon. What do we mean? Now, it means that it has to include the aromatic features, namely at the 3.3, 6.2, 7.7, 8.6, and 11.3. And now we know there are also aliphatic features, in particular the CH stretching mode at 3.14, the CH bending mode at 6.9. Now there are some minor features between 15 and 20 micron, 15.8, 16.4, 17.4, 17.8, and 16.9, and so on. They are seen in H regions, refraction nebulae, planetary nebulae, galaxies. So they are definitely there. But when you consult the chemistry literature, then you can't find any counterparts for these features. It's unlike the other features that you can at least see some approximate correspondence with laboratory spectra. And then there are broad emission plateaus. I already mentioned 8 and 12 micron. There is a weaker plateau around 17 micron. So when we want to discuss this phenomenon, we have to have an explanation for everything. I mean, the whole spectral behavior consisting of these properties. So the most important question is that what is the chemical structure of the carrier, right? I mean, that's what we are trying to do. Now, the most popular theory is polycyclic aromatic hydrocarbons. which have been around for almost 30 years now, or pH for short. Now, pH molecules are well known by the chemists because it's a very simple molecule. It's very common. It consists of only two elements, hydrogen and carbon, and they are pure aromatic. They are all in the form of rings. Okay, so they are a planar molecule. And the pH hypothesis, as I say, going back 30 years now, it can be summarized by this statement. They say that the UIE features are due to the process of infrared fluorescence. That means a simple pH molecule is excited by a UV photon, bring it up to a high electronic state. When it cascades, then it goes through a number of transitions, and including the vibrational modes that you see in the spectrum. And there's a very important Chris Selgren noted that because the 3.13 micron feature, of course, occur at short wavelength, and the interstellar medium is cold, then how do you excite the molecule under such a cold environment? And her theory is that these are excited non-thermodynamically by a single photon. So a single photon hit the pH molecule and take it to a high state, and then when they decay, then you go through these transitions. Now, although this model has been extremely popular, however, I want to summarize here, it has a lot of problems. Okay? First of all, pH molecules are well known. The features, wavelengths are well known, and they are molecules, so the lines are very sharp. Now, however, astronomically, our features are broad. Okay? They are fractional microns wide. And pH molecules are primarily excited by UV. But now we know that in protoplanetary nebulae, there are no ultraviolet photon background. In a refraction nebulae, there are no UV background, and yet we still see the same UIE features. Now, I think this is probably the most significant because the electronic structures of pH molecules are well known by the chemist. So all of the electronic bands are known. So the easiest way to detect the molecule is in absorption. So you point your telescope to some background bright UV sources, some hot stars, and you can look at the pathway in between, and you see whether you see any of these pH absorption features. Now, many people have looked, and none has been found. Actually, the upper limit of abundance of pH in our interstellar medium is 3 orders of magnitude lower than predicted by the infrared observations. So from the infrared, you say you have to have so many pH molecules, but you look at absorption, you don't see anything. Now, because pH molecules are simple, their vibrational and rotational frequencies are well known, so people have also been searching at longer wavelengths to look for specific pH molecules. As of today, none has been found. Okay. The chemists are very unhappy, and astronomers are very happy. They have this theory that to them is very good, but the chemists are very unhappy because the Berkeley group, exactly, they wrote many papers because they know the pH molecules very well, and I quote here: no pH emission spectrum has been able to reproduce a UIE spectrum with respect to either the band positions or relative intensities. Okay. Now, observationally, the shape and peak wavelengths of UIE features are universal. It doesn't depend on what's the temperature of a central star, and so on. Now, because of this problem, then how do you fit the astronomical spectrum? So what they say is that, well, okay, give me a few hundred pH molecules, I mix them up, and I can produce a fit to resemble the astronomical spectrum. Now, to do that, they have to have pH molecules of different structures, compact, linear, branch, as well as different ionization state. I mean, they are either not only neutral, but charged, positive or negatively charged. So this is an illustration of the paper by Skelly. I mean, now because the pH molecules experimentally are well determined. So these are some examples, I think 12 pH molecules and so on. So you see the vibrational bands are all over the place. Okay, they do not concentrate at 3.3, 6.2, 7.7, etc. So to reproduce these bands, you cannot just by a few pH molecules, you have to do something drastic. So in refraction ability, there are three spectra here of three separate central stars of temperature 6,800, 11,000, 19,000. So they are low temperature, very different temperature, and the spectra are almost identical. Okay, so these the spectra are not dependent on the exciting stars, and of course, like I mentioned before, there is no UV at all in this refraction ability. Now, how do they fit them? So the NASA Ames group, they collected comprehensive pH database either by computational or experimental means. They have all the spectroscopic behavior of these molecules. They include neutrals, ions, and so on. They have the size from a few carbon atoms to hundreds of carbon atoms. So they say if you mix these carbon pH molecules, you can reproduce the astronomical spectra. And they are very kind. Their database are completely open, and they even open up their fitting codes, so other people are able to play with it. And so did we. So we used their code and their database to fit silicates. So they're able to fit silicates with no problem. They can even fit the spectrum code. Okay, this is an approach spectrum code. They can fit hydrogenated amorphous carbon, which is a simple amorphous carbon. They can fit some artificial molecules. Okay, this is an artificial molecule that we created. They can fit that. They can even fit artificial features. So we randomly created a number of spectral features. They can fit that. We have more features, 10 features, they can fit it as well. So the model is so flexible, they can fit anything. Okay. So now, I mean, seriously, so obviously what I'm trying to say is that I'm not a believer of the pH hypothesis. Okay. So if it's not, then what is it? Now it turns out that by just two elements, carbon and hydrogen, you can make a lot of stuff. Okay. Carbon and hydrogen, the simplest forms of carbon, is diamond, pure carbon, or graphite, which is also pure carbon. Now, if you add hydrogen, you make it pure aromatic molecules, and on this line, you have the pH molecules. But you can do anything within this triangle. These are called amorphous hydrocarbonaceous solids. Okay? So you bond hydrogen into carbon in different kinds of bonding, either the so-called diamond-like, which is sp3, or graphite-like, sp2, or a mixture of the two, that you can get all kinds of different kinds of hydrocarbons. So now, in the laboratory, you can also try to simulate or create these kind of amorphous hydrocarbons. Now, there are many groups that are doing different techniques, but they're just variations of the same thing. Usually, they just put some hydrocarbons like methane and acetylene or whatever into a chamber, and then you bombard it with energy, either by laser, radio waves, high energy particles, whatever. So you put some energy in there, and you allow the vapor to condense onto some substrate, and you collect the substances from the substrate, and you analyze them. Okay. So the simplest kind of this kind of artificial substance is HAC, hydrogenated amorphous carbon, and that's the chemical structure. So you can see that there's a mixture of rings and chains. So you have one ring, two rings, and they're connected by aliphatic chains. These chains can be in any length or any orientation. They don't have a fixed geometry, and everything is random. Okay? So now so these are only two elements, hydrogen and carbon. Now if you put in something else, for example, you put in some oxygen, then you have a process which is similar to the production of soot in our combustion chemistry. So of course, this technique is now very famous. Many people do it, this technique, because of that was led to the discovery of fluorine in the laboratory in 1985. Now, when Kroto started, I knew Kroto very well because he used to come to Ottawa every year, and he was interested really to create cyanopolyions in the lab. He couldn't he couldn't succeed, but he made fluorine instead. Okay, so of course he got him a Nobel Prize, so that's very good. But the technique is the same. So you have some combustion, depending on what is in the initial mix that you create. If you have oxygen or you have nitrogen, or you just have pure carbon and hydrogen, then you create all kinds of these artificial hydrocarbons. Okay. Now, of course, once you create them, you can take a spectrum, right? So this is a laboratory spectrum of these hydrocarbons, amorphous hydrocarbons. And below, I put a infrared spectrum of a planetary nebulae. And you can see that there are some similarities. Okay? It's not a one-to-one correspondence, but they look similar. Okay? So that we are looking at something probably similar. So we have, this is another laboratory in Germany. They created these artificial particles and take the infrared spectrum. And this is again the same infrared spectrum of a planetary nebulae, and you can see the correspondence. So now, well, is it pure hydrogen and carbon? See the pH molecule, or it could be with nitrogen. Now, some people are keen about having nitrogen, and for example, one possibility is tholins. Now, tholins, some of you may know, was first produced in the lab by Carl Sagan in Cornell, and he basically put this similar kind of technique. He bombarded the sample with UV by putting in nitrogen, ammonia, methane, and then to create this artificial brownish substance called tholins. Okay? Or if you use a different kind of techniques, where you put in not a nitrogen, for example, starting with HCN, you get HCN polymers. Now, actually, these things are common in nature. Actually, we have a lot of organics on Earth, as I described at the beginning, in the form of coal, oil, and so on, and kerosene. And if you look at their chemical structure, they are amorphous hydrocarbons. Okay? So, now, of course, on Earth, they are the result of life. Okay? Now, what is kerosene? So kerosene is a random array of aromatic islands connected by aliphatic chains, but they are not pure. They have all kind of impurities in the form of sulfur, nitrogen, oxygen, and so on. And they are a solid. They are not soluble, and you can find them in sedimentary rocks in the upper crust of the Earth. This is the chemical structure of kerosene. Okay. So the dark areas are the aromatic rings, the lines are the aliphatic chains, and you can see that the islands can be in 4, 2, or whatever number of rings, and they are connected randomly by aliphatic chains. Okay. So it's very, very interesting. This is a laboratory in France, in Saclay. You know, France used to be a big producer of coal. Okay? So they were very keen about coal. They did research in coal. There's some coal researcher. They somehow, I don't know how, they found out a paper on the protoplanetary nebulae, and they say, wow, this spectra looks like a spectrum of coal. So this is a 3.3 micron feature. This is 3.4 micron feature. There's the 8 micron plateau. That's the 12 micron plateau. Now this is crazy, right?
Wow.
Well, there's a group in Italy. They study oil, and they extract fragments of oil, and then they took infrared spectrum. So this is spectrum of coal, different kinds of oil, and this is the protoplanetary nebula spectrum from us. Okay. Well, it's not 100% correspondence, but you can see some similarities there. Right? Okay, so esters. I mean, same thing. I mean, these are just oil extracts, right? So these are the chemical formula of the oil fragments that they were using. So coming back to the UIE phenomenon, so we have these aromatic features, we have some aliphatic features, we have some identified features, we have some plateau features. So what's the structure? So we have to be able to explain all of them. So this is NCC 727. So the first step for us is that we decompose the spectrum, okay, to separate them. Okay. And it turns out that most of the flux are coming out in the continuum, which are probably due to a macroscopic solid state particle, one of its carbon or something. And then outside of that, which is 65%, the aromatic material accounts for 13% of the energy, and the aliphatic material accounts for 17% of the energy. So definitely not everything is aromatic. Okay? So what do we propose? So we propose the carrier is a mixed aromatic, aliphatic, organic nanoparticle, or muon for short, and this is one example of possible chemical structure. So you can see the difference is that we have islands of aromatic rings. They are connected by aliphatic chains. We have impurities such as oxygen or nitrogen or even sulfur, and that is possible carrier for the UIE phenomenon that was published in 2011. Now, coming back to the long wavelength bands. Now, I mean, as I said before, the features between 15 and 20 are never identified. Okay. Now, what can be due to? Now, the chemists were interested in principles. They are only interested in what is the fundamental thing about these vibrations. So once they determine from simple molecules, these are either due to stretching or bending, they are very happy. Okay? They don't care. And our nature is more complex. We have larger molecules than just a few. Now, what if you have a large molecule like this one? Then, of course, the vibrational modes are very complex, and those were never studied by the chemist. You can see from here, this is the feature 15.3 of this artificial molecule, and you can see there are lots of the so-called deformations of the skeleton of the carbon aromatic center part, plus some vibrational mode of the aliphatic side. Okay. So these things have to be studied. I mean, that's why we now want to do quantum chemistry calculations, to look at larger molecules so that we know what's going on when you have a larger molecules when they are vibrating. Now, this is a completely different structure. I mean, also artificial, and these are less aromatic and more aliphatic. And again, you can see that they have features due to various combination of vibrational modes. Now, the more recent discovery is fluorine. Now, this, of course, very interesting. Now, the fluorine, being a simple symmetric molecule, have 4 infrared bands, and they are very easily detected. I mean, I'm very sorry. I should have seen it, but I searched for it, and we published papers, maybe a tentative detection, but we didn't check the SPISA database, which Chemi did, and they detected C60, okay, with no problem at all. Okay, so now you look at the C60 spectrum. Now, not only they have C60 and C70, they have plateau features. So there is an 8 micron plateau here, 12 micron plateau there, and there is, I'll talk about that later, 30 micron. So these things are in common with the UIE phenomenon. So they are something, they are sharing something. Either the pH, the fluorine molecules are the products of whatever substance that created these plateau features. So in propylene nebulae, it's the same. We can see the fluorine sources. We can see the 8 micron plateau, 12 micron plateau. So these are the C60 sources always have the plateau features. Now obviously, most people realize the pH hypothesis have problems. So the pH proponents will say, well, okay, well, whatever you are saying, these are astronomical pH. That's what they say. I disagree. I think this is a question of semantics. You cannot call something different, astronomical, something else. Okay, now they are very different. So the moon are amorphous. They are not no fixed structure like pH. They contain rings of different sizes and chains of different lengths and orientations. They have impurities. They are not two-dimensional. They are three-dimensional, and they don't have a fixed even content. Now, so you cannot be just like calling hydrogen peroxide astronomical water. I mean, which is I don't think is correct. Okay. No, I mean, I think we have a serious test here. I mean, is it pH or is it moon? So is it a free-flying molecule or a solid? I mean, that's a huge difference. We're talking about simple molecule or is a complex solid. Is the chemical structure regular and like pH, or they are amorphous? So is it a pure aromatic, or is it a mixed aromatic aliphatic? Is it three-dimensional or two-dimensional? Is it small or is it large? Okay, is there pure hydrogen carbon or with impurities? So are they pure rings or they have functional groups? I mean, these are clear-cut differences. You cannot say, oh, wow, what we are seeing is just a modification of the pH hypothesis. They are not. Okay. Now, okay, another thing is the excitation, which is a more difficult problem. The 3.3 and 7.7 micron radiate at a short wavelength. That means they cannot be radiating thermally. They cannot be excited thermally. So you have to find some way to excite them non-thermally. Now, of course, if you have a simple molecule, then you get excited by single photon. But you have a larger molecule, then it's more difficult to excite it. I mean, so we have to keep the molecules, the compounds, small in terms of nano size, or there is another mechanism like chemical excitation, which was proposed by Dewey and Williams. Now, another interesting thing is how do they form? Now, theoretically, molecules either use acetylene or benzene or C60. I mean, theoretically impossible to form because in the circumstantial environment, you are talking about density which are lower than any vacuum you can produce in the laboratory on Earth. Okay, you are talking about pure vacuum, and so then you cannot rely on ordinary chemistry to form these compounds, but you see them form. I mean, there is absolutely no doubt about them observationally because we see them form for probentionary on time scale as short as hundreds of years. Most remarkably is novae. In a novae, after ejection, you're talking about weeks, and you see the 3.3, 3.4, 8 micron plateau, 12 micron plateau, and they are not observed continuously, but their observations are separated by weeks. So we know these organics are formed on the time scale of weeks. Now, not only they are formed quickly, or they can be seen to be formed quickly, they are everywhere. Now, you look at the diffuse in the aluminium, and you look at some bright infrared background sources, and you can see the absorption spectrum due to methyl and methylene CH stretching. So this is a line of sight to the galactic center, and now these aliphatic features have been seen in external galaxies, in the other galaxies, and so they are everywhere, not just in the Milky Way. So this is the 3.4 CH stretching due to aliphatics. This is the 6.9 bending mode due to it is diffused interstellar aliphatics, and because absorption spectrum is very easy to interpret, there is no excitation mechanism. You see an intensity, you can derive a column density. It's very simple. So 15% of the carbon are in aliphatics. So now carbon is a very common element in the universe, and we are seeing that 15% of all the carbon are in aliphatics. Okay? This is not a trivial thing. Now you look at M82, for example, the Japanese satellite, they mapped the whole galaxy of M82. These 3.4 microns features is everywhere. Now we're going back to the solar system. Okay, now, I mean, as I mentioned earlier, traditionally we think the solar system is made of metals, ice, and minerals. And now, more and more missions have been carried out, including sample returns. Once you have a sample return, you can do a lot in the laboratory. I mean, these are some of the techniques that have been used. Of course, we can do infrared spectroscopy by astronomical telescopes. And since the 40s, we know that there are organic molecules in Uranus, in Neptune, and Titan, and so on. And so you have methane, acetylene. And all these things can be done remotely by astronomical observations. Now, you can also do sample analysis. I mean, the meteoroid is something that we can put in the lab because they fall out from the sky. They originated from either comets or asteroids. And you find that they have very complex organics in them, including amino acids. Nowadays, you have over 100 amino acids identified, whereas our body only needs 20. Okay? So these are amino acids, definitely nothing to do with living organisms on Earth. They were made abiologically, and they were not used in our biochemistry, but they are available nevertheless. Oh, by the way, so every compound of organics that is known in the laboratory have been identified in meteorites. So they are non-terrestrial in origin because we know that on Earth the proteins, amino acids are only left-handed, but in meteorites they are both right and left-handed, and they have we have only 5 nucleobases in our living organisms, but they are more in meteorites. Now, in addition to this so-called soluble component, there is also an insoluble component. So there are parts of the meteoroid that cannot be dissolved in acids, but you can still try to analyze them by either destructive or non-destructive means, and the chemists are able to determine they have aromatic and aliphatic structures, and there is by abundance there is a chemical formula. So they have not only hydrogen and carbon, they have oxygen, sulfur, and nitrogen, and so on. Now comets, of course, we can do infrared spectroscopy, but with, say, Rosetta or Stardust, you can go there actually and you can collect the samples. So this is a recent paper in Science on Rosetta, organic samples, and they are definitely, comets are definitely not dirty snowballs, but they have organics. This is the 3.4 micron feature that's similar to what we're seeing in protoplanetary nebulae. In the planetary dust particles, they are good because they can be collected in the upper atmosphere. You can bring them back to Earth. You can put them in the lab. So this you can see again the 3.4 micron feature corresponding to the aliphatic CH stretching mode. Titan, well, because of Cassini, they sent a probe down to the surface of Titan. We know that there are a lot of organics in the atmosphere of Titan, and also in sand dunes and in lakes and so on. Estimated the total amount of hydrocarbons is more than the total hydrocarbon reserve on Earth. So what are they? The planetary scientists, because of their community, they always believe in tholins. That's what they think. They are tholins. So what is tholins? I mean, it's really very similar to, it's just one form of the amorphous hydrocarbons. I mean, except they have a lot more of nitrogen. So in the Titan atmosphere, you can, this is a paper by a team in Korea. You can see the 3.4 micron features, the Titan haze, and they have the profiles are very similar to those in the comets and in protoplanetary nebulae. So the old paradigm is that the solar system are primarily made up of things that were made after the formation of the solar system, because at the beginning it was everything was broken down into chemical elements. Now we are not so sure anymore, because of pre-solar grains. Okay? Now we can hold in our hands solid grains. For example, the first one found was silicon carbide, being manufactured by AGB stars. They went across the Milky Way galaxy. They were deposited into the early solar system. They fell on Earth and collected by us in the form of meteorites. So we know that products that is identified by isotopic ratios, products of stars can come across the whole Milky Way galaxy and ended up on Earth. If that were the case, how about organics? I mean, we know that stars make organics. Can they survive the journey through the interstellar medium and fallen on Earth after they entered the solar system? I want to spend a few minutes to talk about the other unexplained spectroscopic phenomena in the ISM. These include the diffuse interstellar bands, the 2200 angstrom feature, the extended red emission, 21 and 30 micron features. I can't say very much, I'll just be very quick. So the DIB has been 100 years old, and they have hundreds of lines, very strong bands, and as of recently, all but two are unidentified. The other two identified are now suggested to be ionized fluoride. Okay. So these are almost definitely electronic transitions of gas phase molecules, but not gas phase molecules that we are familiar with. Because if we had seen these molecules in the lab before, we would have been able to identify the spectrum. So these are carbon-based carriers, and we don't. They probably have some kind of radical, and that we do not have on Earth. So my hypothesis is that maybe they are broke down products of muons. And the 2200 angstrom features are seen everywhere. Oh, by the way, the DIBs are also seen in external galaxies. So is the 2200 angstrom feature. They are everywhere. They are now also seen in the planetary dust particles. So this is the same feature in the IDP as well as in the diffuse in the stellar medium. The 21 micron feature, a very bright feature. We don't know what it is, other than it's probably carbon-rich substance. And the 30 micron feature, this is the profile of 21 micron feature mostly seen in protoplanetary nebulae. The 30 micron feature is more common and is also very bright, a lot of energy. In some cases, 20% of the total energy is coming out in this band. And so these are the 8 and 12 micron plateau. These are 21, 30 micron feature. The ERE is a photoluminescence phenomenon. They are also seen in external galaxies, and we think that this is due to some semiconductor, but not sure exactly what it is. 4% of the energy absorbed by dust in the stellar medium are emitted in the form of ERE, so there is a major carrier or component of the stellar medium, most likely due to is made of carbon or silicon, so it could be some form of amorphous organics. Okay? Now, although I'm not offering any solutions to this phenomena, I'm just saying that it's quite likely these unexplained phenomena are also related to organics, because organics are something that we don't know much about. So in summary, we now know in the past 20 years or so that organics are everywhere. They are in our solar system all the way to the interstellar medium and to external galaxies. And the detection of UIE bands in the redshift of 2 suggests that synthesis of organics occurred almost right after the synthesis of carbon. And the observed features are consistent with the carrier, being a complex organics of mixed aromatic aliphatic structures. And protoplanetary nebulae and planetary nebulae and novae are the only objects that we are able to see these compounds being formed. And they are formed very efficiently. These under very low density environment and over very short time scales. So complex organics are routinely made by ordinary sun-like stars. The detection of pre-solar grains in meteoroids suggests that the product of stars can travel across the galaxy and be deposited on Earth. So if they were organics being made from stars and enter our solar system, they may explain the origin of the complex organics in meteoroids or in comets. And because the Earth was subject to a huge bombardment in the first 500 million years of our history, possibly that those bombardments carry with them a sizable amount of organics. So we now know that macromolecular, meaning they are not simple molecules. Organics are seen in meteoroids, in interplanetary dust particles, in comets, in planetary satellites, and they are very similar in chemical structure to those seen in planetary nebulae. So the question is that to what extent the solar system was enriched by stellar organics. So also to what extent the early Earth was chemically enriched by extrasolar organics. So these are some references I put up here. I want to note there are also two recent reviews by Anthony Jones and Lucy Series, and they are more or less talking about a similar thing that I've been describing today. Yeah, that's all. Thank you very much.